I'm not quite sure exactly. Let's try to use a method that we have just introduced or we have just reviewed to solve this non-homogeneous ODE. As you see, it's already written on the slide. Also, you may use some method that's not on the slide. So the homogeneous equations are obviously easy, and they always have general homogeneous linear equations have general solutions. It's not always the case for non-homogeneous solution. And then, but for this one, we see there is a little trick. And again, we are focusing on state space methods. So if you recall, you probably have solved this using Laplace transform before. But this L here is not Laplace transform. Let's look at what this method is. 有没有人知道记得以前学过的方法 I was asking whether anyone recalled the method they have learned before. 有没有？我给你们一个机会说啊，不要想，想不到我再讲。有吗？
其中一个方法可以用 Laplace。
所以你们有印象的还是 Laplace 的话，是不是？
有其他方法 ，Laplace 是比较可攻的。
OK，如果叫你用 Laplace 转换，你算得出来吗？好，没关系。Let's look at this method, okay? We define an operator. This operator is defined as derivative minus 1. What happens if we take the derivative of exponential function and minus 1 times the exponential function? It becomes 0, right? So if we use this operation, if we use this operation on this exponential function, it becomes 0. And it turns our equation to 0 on the right-hand side, but on the left-hand side, it becomes a third-order differential equation. That's what happens. It used to be a second-order differential equation. If you take this operation on the original equation, it becomes a third order, and when you have a third order, you have 3 roots. If you have the roots, you have the general solution, and if I block this, I was supposed to ask you what is the general solution, but here it's written out. In this case, you have the combination of these 3 factors. So this is just an example of how we might solve the non-homogeneous ODE. Plots of the 3 parts, and then if we have initial conditions, in the same way we would do for homogeneous equation, we can solve for the coefficients. And the coefficients are 1/4, -1/4, and 3, -3/2. So we finished the linear homogeneous equation and non-homogeneous equation for the case with one variable. The coupled differential equation means that we have two or more variables, such as this. Instead of having just y, we have x1, x2, and you can have it up to any sort of order. Okay, so what kind of system will look like a coupled differential equation? And the answer, there should be many different solutions to this question. 有没有听懂问题？就是什么时候我们会遇到这样子的一个样子的联立的 ODE？ 后面那个边我好像没有问过。你啊，你这边。我的问题是什么时候会看到做联立的，就是有两个变数以上的 ODE？ 刚才都考虑一个变数。Okay, that's a possible solution. Is when we have two masses, we will need two variables to represent the position of different masses in the system. That was actually supposed to be an easy question. And also, if we want to convert a second order differential equation to an equation that we can simulate, we usually convert it to a first order multivariable differential equation. 所以我们二阶转一阶也会从一个变数变到两个变数，或是高阶转一阶。然后 and then the convenience is that we can, if it's first order, this is a first order differential equation. And if it's a first order differential equation, we can write it in matrix form. And this is also why linear algebra is